All right, ladies and gentlemen, let's continue our review of chemical equilibrium. Last time we were talking about the concept of the reaction quotient, and that is to check if a system is at equilibrium, I can just plug in any values given to me and into what we call the reaction quotient Q. Same thing as K. We're just taking the numbers, not knowing if we're at equilibrium. And if they match K, then we say we are at equilibrium. If they're less than K, then we still need to make more product to reach equilibrium. If we are greater than K, then we've passed equilibrium. We got to come back down a little bit. And so this will help us determine which way the reaction is still moving. Now, today we're going to talk about systems that have reached equilibrium and what happens when I disturb them. So the idea is known as Le Chatelier's principle. And it states that when a chemical system is at equilibrium and it is disturbed, it returns to equilibrium by counteracting the disturbance. Now, in this case, when I say the word disturbance, we're actually talking about four possible scenarios. Number one is I change the concentration of the chemical species at equilibrium. Number two is changing the pressure of a system. Number three might be changing the temperature. Number four would be adding a catalyst. And we're going to talk about how I think about these disturbances and what a system will do to reestablish equilibrium. This first part is all about changing concentrations. And if I think about a system being at equilibrium and then I change the concentrations of anything in that system that's equilibrium, that is present in the equilibrium expression, then really all I'm doing is I'm no longer at K, and now I'm at some Q. And so I'm just going to compare Q versus K again and plug those in. But I can kind of think about it just qualitatively in terms of balancing out what I have. And so whatever change is done to one side, the same has to happen to the other. And this makes the changes predictable. So for example, if I add reactants or products, then the opposite side is also going to increase. What's a little bit trickier is whatever I add in, so let's say I add a reactant, that reactant is going to go up just slightly. But any other reactants that are in the reaction are going to go down because they're going to be consumed as they're used to produce the products as that product side increases. The opposite is true for removing the reactants and the products. The species removed will slightly decrease. Any species on the same side will increase because the reaction is going to have to try to fill in that hole, that decrease in reactant. And so the opposite side is also going to decrease. This sounds trickier than it is, but just take your time thinking about it and it should be okay. And we had a couple of practice problems. So here's our first practice problem. Let's consider the reaction between H2 and CO to form methanol, CH3OH. I want to know what will happen to the concentration of H2, CO, and CH3OH when two changes are done. Now what I would do is I would pause the video here, kind of write your answer, and then continue playing the video and see if your answers match my explanations. So here we go. If I look at A, I'm going to add H2. H2 is a reactant, which means that if I add to the reactant side, the product side has to go up. So immediately I know the CH3 is going to increase. Because I added H2, it is also going to increase. But for the CH3OH to go up, I must have used some of the CO that reacted with that extra H2. The CO is going to go down. So H2 goes up, CH3OH goes up, CO goes down. Now part B says what will happen if the concentration, or if CO is removed. So if I take out CO, it's going to go down, then obviously it's going to go down. That means the CH3OH has to go down because whatever happens to one side has to happen to the opposite side. But anything on the same side of the CO will go the opposite direction. So we have the CO going down, the H2 goes up.